In this presentation, I'll be explaining the boost converter or step-up converter and the working of a boost converter and the design of the inductance as well as the capacitance and a problem based on this design as well as one application of the boost converter for the maximum power point tracking of the solar PV system. That will be explained in the coming slides. Now coming to the boost converter circuit topology, it's also called step-up converter, and this is the circuit topology as such. Here, of course, the input side there is an inductor, and this can be considered as a single pole double throw switch as such. The two position, either one or two, and there is a capacitance across the load. Therefore, this is the load, and this is the capacitance, and this is the circuit topology as such. Now, for example, the switch, the single pole double throw switch, SBDT switch can be either it can put into position 1 or it can be put into positions 2. For example, if this is putting position 1, the equivalent circuit is like this one. And then the voltage across the inductor is same as the input voltage VD. And the the current through the load is same as the, of course, it is equal to that is being supplied or the discharge current of the capacitor. Therefore, this is the circuit topology as this SPDT switch is put in the position 1. Now, if you consider the same SPDT switch put in the position 2 here, the corresponding equivalent circuit is this one. And here, therefore, here during the position 1, the energy will be stored in the inductor, and during the positions 2 here, the circuit that will be changing to that one. Therefore, this is the circuit, and here the whatever the stored in the energy or that will be transferred to the load. Therefore, that boosting action is taking place, and this is the circuit equivalent circuit when this SPDT switch is put in the positions 2. Now, the SPDT switch can be realized by using, of course, a MOSFET as such. Therefore, here, when MOSFET is on, mean it is equal to put in the position 1, and when MOSFET is off, it is putting into positions 2. Therefore, these are the two positions of the switch and the corresponding equivalent circuit as such. Position 1 equivalent circuit, and or the MOSFET, when switch is MOSFET is on here, the input voltage VD will be coming across the inductor, and energy will be stored in the inductor, and when the MOSFET is off here, whatever the energy stored in that can be transferred into the load. Therefore, this is the equivalent circuit corresponding to the off position of the switch. Continuing the boost converter in a continuous conduction mode or CCM here. Here, why it is called CCM means the current through the inductor never goes to zero, or always is more than zero. In that case, we call it as continuous conduction mode here. Now, coming to the same circuit as we already explained here, at the input side there's an inductor, a switch is there, and here a diode. Of course, there's a capacitor is there, and that is coming across. Therefore, this is the circuit diagram of a boost converter, and let us see the equivalent circuit corresponding to the two positions of the switch. When switch is on here, the equivalent circuit is this one, or the inductor voltage or inductor is coming across the supply voltage VD. Therefore, the voltage across the inductor will be same as the VD, the voltage VD here. And since the voltage across the inductor is positive, since LdI by dt equal to the voltage across the inductor VD, or DIL by dt equal to VD by L. Since VD is positive here, in this case, since during that period VD is positive, that one, the current is building up with a positive slope. The current through the inductor is building up with a positive slope. And during that period, the energy will be stored in the inductor. When switch is off here, the corresponding equivalent circuit is this one. Therefore, this is the equivalent circuit corresponding when switch is off here. Therefore, in that case, the input voltage is VD, and here the average output voltage equal to V0, and the voltage across the inductor equal to VL. Now, applying the Kirchhoff's voltage law here, we can see that one. Here, the voltage across the inductor is given by VD minus V0. VD minus V0 is the voltage across the inductor. Therefore, that is VD minus V0 is actually minus of V0 minus Vd. Of course, we'll see the later. For that, this is a negative voltage that is coming across the inductor. Since the voltage across the inductor is negative, here this voltage is negative, dIL by dt is negative. That is why when switch is off here, the current through the inductor is decreasing with a, of course, that is decreasing, and it has got a negative slope here. And here again coming back to this position, therefore this current will be same as this current, or the current through the inductor at when time t equal to 0 is same as the current the inductor at the time t equal to Ts. Therefore, that is in continuous conduction mode. This is the inductor current and this is the voltage across the inductor. And these are the two equivalent circuit when switch is on and this is the switch is off. And therefore, this is a continuous conduction mode. Switch is on here and switch is off this one. And the same waveform is shown here. When switch is on, the voltage across the inductor is given by the Vd, it's a positive voltage. And when switch is off here, the voltage across the inductor equal to Vd minus V0, or the same thing can be written as minus of V0 minus Vd. Now let us see the volt second balance of the boost converter and as well as the inductor voltage. Inductor voltage I already explained in the previous slide. That is when switch is on here, the corresponding voltage across the inductor is same as the input voltage Vd. And when switch is off here, the corresponding voltage across the inductor is given by Vd minus V0. Or of course that can be written as minus of V0 minus Vd, and it has got a negative voltage. Therefore, this is the voltage across the inductor. And the corresponding current through the inductors also I already explained. Since the voltage is positive, the current is having a positive slope. And when voltage across the inductor is negative, it is got a negative slope. Therefore, this is the inductor current. And of course, the average inductor current is same as this is the average inductor current. And we'll see the corresponding voltage across the inductor is given by L dIL by dt. Or during the on period, the voltage across the inductor equal to Vd. And if you substitute that one, Vd, voltage across the inductor Vd equal to L dID by dt, or dIL by dt, that is equal to, it has got a slope, during this one, the slope is equal to, when switch is on, the slope of the current through the inductor is given by Vd divided by L. And during the off period, that is when the switch is off here, the voltage across the inductor is given by Vd minus V0, or minus of V0 minus Vd. That is equal to L dIL by dt, or dIL by dt equal to minus of V0 minus Vd divided by L, or it has got a negative value. That is why it is getting a negative slope. Therefore, the rate of change of current through the inductor when switch is off, it is equal to minus of V0 minus Vd divided by L. It has got a negative slope. Therefore, here this current is same as this current, meaning that in any switching converter under steady state condition, the net changing inductor current over one switching period must be 0. Meaning that the current at this point, at the IL at 0, should be same as IL at Ts. Therefore, in steady state condition, initial and final value of the inductor current are equal. This current is same as this current. Or you can say that IL at Ts should be equal to IL at 0. Now again coming back to the basic equation of VLT equal to L dIL by dt. Or from this equation, if you integrate, we'll be getting what is the current. Current through the inductor corresponding to this point, ILTS is given by 1 by L integral 0 to Ts VL dt, VLT dt plus the initial value of the current IL0. Therefore, this is the value of the current when at Ts. Equation for that one. Therefore, if you take IL0 this side, IL at Ts minus IL0 equal to 1 by L integral 0 to Ts VLT dt. Since the IL at Ts is same as IL at 0 here, both are same, this will become 0, or 1 by L integral 0 to Ts VLT dt should be equal to 0, meaning that integral 0 to Ts VLT dt is equal to 0, or the average value of the voltage across the inductor over one switching period must be equal to 0. That is the concept of volt second balance. Or if you see that later, we see that this area is equal to, this area, positive area should be equal to the negative area. Therefore, the net volt, the product of voltage and time, that's called volt second. That unit is flux. The net change in flux should be equal to 0. Otherwise, the core gets saturated after few switching cycles. Therefore, in order to prevent that one, the average voltage across the inductor over one switching period should be equal to 0. Meaning that this positive area should be equal to the negative area. Thus, under steady state operation, the integral of the inductor voltage over one switching period must be equal to 0. because the unit of volt, the product of voltage and second, the unit is equal to flux. It is as or flux linkage. It is a flux linkage. So for the net change in flux linkage or net change in flux should be equal to 0. For integral 1 by L 0 to Ts VLT dt should be equal to 0. Integral 0 to Ts VLT dt should be equal to 0. The above equation says that the total, that is the product of voltage and time, that is product of voltage and time is nothing but the area. For the net area, that is positive area should be equal to negative area, then only the net area over one switching period should be equal to 0. The above equation says that the total area or the volt second under under VLT waveform, that is inductor voltage waveform, must be equal to 0. Or here the positive area should be equal to the negative area, so that after one switching period the net volt second balance or volt second should be equal to 0, or net change in flux should be equal to 0. Otherwise the core gets saturated after a few switching cycles. Therefore, in order to prevent that one, the volt second balance should be obeyed, and this is actually derived from the constant flux theorem. Here coming to this one, this area should be equal to this area, means the net volt, this is a positive area, negative area, or the sum of this one should be equal to 0, or positive area should be equal to negative area. Now equating that one, Vd into T on positive area plus minus of V0 minus Vd, that into this length, or Ts minus T on, which is equal to off period, that should be equal to 0, or Vd into T on minus V0 into Ts, V0 into Ts plus Vd into T on, Vd into T on plus again Vd into Ts, Vd into Ts here, minus Vd into T on should be equal to 0, or from this equation we'll be getting V0 into Ts minus T on is equal to Vd into Ts, or V0 by Vd equal to Ts divided by Ts minus T on, or dividing numerator and denominator by Ts here, it will be getting V0 by Vd equal to 1 by 1 minus T on by Ts, which is equal to the duty cycle D. Therefore, V0 by Vd equal to 1 by 1 minus D, where D is equal to duty cycle T on by T. Therefore, here this is a boost converter or a step-up converter. For example, if the duty cycle is kept as 0.5, if you make duty cycle equal to 0.5, it is equal to 1 by 1 minus 0.5, or output voltage equal to 2 times the input voltage. Average output voltage equal to V0 equal to 2 times the input voltage. Therefore, by changing the value of this D, as D increases, the output voltage increases, or as you change the value of the D, the average output voltage can be changed, or basically the output voltage will be, average output voltage will be more than the input voltage. That is why it is called a boost converter or a step-up converter. The basic relation of average output voltage and input voltage equal to V0 by Vd equal to 1 by 1 minus D, where D is the duty cycle on period divided by the total time period, Ts. Therefore, the average output voltage divided by the input voltage equal to 1 by 1 minus D. D is the duty cycle, T on divided by Ts. Continuing the volt second balance concept of boost converter. In continuous conduction mode, neglecting the power loss associated with all the circuit elements and the input, then if you neglect the power loss in the elements like inductor, capacitance, switches, etc., input power should be equal to the output power. Input power is nothing but Vd into Id. Output power is given by average output voltage V0 into I0. For Vd Id should be equal to V0 I0, or we can say that one V0 by Vd equal to Id by I0, where I0 is the average output current and Id is the average input current. Now V0 by Vd already we derived 1 by 1 minus D, where D is the duty cycle, T on divided by Tc, and then this current Id by, so here I0 by Id is nothing but 1 minus D. Therefore, this is the relation for output voltage, average output voltage divided by input voltage equal to 1 by 1 minus D. And average output current divided by average input current is equal to 1 minus D. Therefore, D is the duty cycle. Here, in continuous conduction mode, this is a step-up converter or a boost converter is equivalent to a DC step-up transformer, like it's a DC transformer which is equal to step-up. Therefore, this is the output current divided by input current equal to 1 minus D. It is equivalent to a step-up transformer as such. Therefore, output voltage is AC output voltage is more than input voltage. Like that, when it's a counterpart of that one, or it is equivalent to that one, it is an equivalent to the DC transformer, like step-up transformer, when it is operating in a continuous conduction mode. Therefore, V0 by Vd equal to 1 by 1 minus D, and I0 by Id equal to 1 by D, where D is the duty cycle on period divided by the total time period Ts. Now let us see the design of these values of inductor L and capacitor C. Now coming to the first inductor L as such, first one here, and these are the this is the circuit topology as already explained here. Inductor, capacitance, the switch is coming here. This is the input voltage and average output voltage will be 0, and there's the diode is the load is resistance equal to R. So this is the circuit topology, and the voltage across the inductor equal to, when it is on it is equal to VD, or when it is off it is equal to VD minus V0. So this is the voltage across the inductor. And what we are assuming is that load current equal to constant. A constant load current I0 is being assumed. And the inductor current, when it is positive, the current is building up from I1 to I2. And when it is negative voltage coming across the inductor, it is di by dt equal negative. Current is reducing from I2 to I1. Therefore, this is the current through the inductor. And this is the voltage across the inductor. And if you see the capacitor current, when switch is on here, the load current is met by the capacitor. The capacitor is discharging, or we can say that IC equal to minus I0, because we are assuming constant load current. That is why when switch is on here, the capacitor is supplying the load current, that is equal to minus I0. And when switch is off here, the corresponding current, input current, that is the load IL minus I0 equal to IC. IL minus I0 equal to IC. That is why IL minus I0 means here this current will become, here it is equal to, this is IL equal to I2 minus I0. Current is decaying, current through the capacitor is decaying from I2 minus I0 to I1 minus I2. It's actually IL minus I0. That is the current through the, during that period capacitor is charging. Therefore, when switch is on, the capacitor is discharging with a constant load current, and when switch is off here, the capacitor is charging, that is from I2 minus I0, and that is here, in here the capacitor current when here it is equal to I1 minus I0. Therefore, this is the capacitor current, and this is the voltage across the inductor. This is the load current, and this is the voltage across the inductor. Now coming to the basic equation of the change in inductor current, delta IL. Delta IL is means that it is equal to I2 minus I1. Therefore, the change in current is given by I2 minus I1, or that is equal to delta IL, or delta IL equal to I2 minus I1. And this change in current, the slope of this current is given by, that is VD by L. VD by L is the rate at which the current is changing, or the slope of this current, or VD by L. And for this time, that is on period, how much is the change? That is equal to actually delta IL. For VD by L, that into the on period, that is the total change I2 minus I1, or VD by L into T on equal to dTs. D is a duty cycle into Ts is the time period. For substituting that one, the changing inductor current delta L is given by dVd divided by Ts, or 1 by Fs into L. Fs is the switching frequency, or 1 by Ts. Therefore, the corresponding equation for the changing inductor current is given by dVd divided by Fs into L, or the inductance value L is given by dVd divided by delta L into delta IL into L, or dVd divided by Fs into, that is L, the inductance L is given by dVd divided by the switching frequency Fs into delta IL, the change in inductor current. Therefore, this is the way in which you can design the value of the inductance based on the what is the permitted value of the change in inductor current. That is substituted. Of course, this is the switching frequency, D is the duty cycle, and Vd is the input voltage. Therefore, the inductance value is given by dVd divided by Fs into delta IL. Now let us see the design of capacitance, or what is the value of the capacitance. Now let us see the design of the capacitance C. And this is the capacitor voltage already explained in the previous slide here. When switch is on, it is capacitor is supplying the load current, because load current is constant. That is the capacitor current is opposite to this. Therefore, it is equal to minus, the capacitor current is equal to minus I0. And when switch is off here, the capacitor current is nothing but the inductor current minus the load current I0. Therefore, it is changing from I2 minus I0 to I1 minus I0. Therefore, this is the capacitor current. And if you see the voltage across the capacitor here, and during the discharge of the constant current I0, there will be a dip in output voltage, which is equal to it is changing from VEC, or delta VC is the change in voltage due to a constant current I0. Or in order to find out how much the voltage is dipping here, we have to the change in capacitor voltage delta VC is because of the constant discharge current I0 from the capacitor for a duration of the on period, T on period. Therefore, in order to calculate that one, delta VC is given by, VC0 minus VC T on, that is the voltage at C0 minus VC at T on, which is nothing but 1 by C integral 0 to T on, here this period, into the the current through the capacitor, which is equal to minus I0 dt, or that substituting here, of course, the magnitude equal to I0. That is why it is substituted magnitude only I0. Therefore, delta VC is given by 1 by C integral 0 to T I0 dt, or we can get I0 into, that is I0 means total, the load current, constant load current I0 into the on period T on divided by C, or I0 into T on equal to dTs divided by C, or is equal to D into, which is equal to D into, this is equal to I0, d I0 divided by Ts equal to 1 by Fs, or Fs into C. Therefore, the change in capacitor voltage delta Vc is given by d I0 divided by Fs into C, where d is the duty cycle, I0 is the constant load current, Fs is the switching frequency, C is the capacitance. Therefore, the capacitance value can be calculated. It is equal to d I0 divided by Fs into delta Vc. Therefore, this is the way how the capacitor is being designed, which is equal to, the capacitor can be designed based on the permitted voltage ripple in the capacitor, or permitted output voltage delta Vc, which is that, if you know that one, if you know the switching frequency and duty cycle and the load current, then you can calculate, of course, you can calculate what is the capacitance value to be connected across the load. C equal to d I0 divided by Fs into delta Vc. Now let us see a problem based on the boost converter. A boost converter has an input voltage 5 volts, and the required average output voltage is 15 volts, and the average load current is equal to 5 amperes, and the switching frequency is 25 kilohertz, and inductance value L equal to 150 microhenry and C equal to 220 microfarad, and determine the duty cycle, a ripple current of the inductor delta IL, and the ripple voltage of the capacitor delta Vc. For D, first we have to find out what the duty ratio. For that, input voltage is given as 5 volt, and the average output voltage is given as 15 volts, and the basic relation of output voltage and input voltage equal to V0 equal to Vd divided by 1 minus D, or V0 equal to Vd divided by 1 minus D, and substituting that one, we can get the D value, output voltage equal to 15 and input voltage is equal to 5, or substituting that one, the duty cycle, we can get it as 10 divided by 15, or 0.6667, or 66.67% is the duty cycle. Second one, ripple current of the inductor. The basic relation of the ripple current is given by dVd divided by Fs into L. D is the duty cycle, Vd is the input voltage, Fs is the switching frequency, and L is the inductance value. All these values are given. Therefore, you can substitute that one. D is already calculated. 0.6667 into, of course, Vd equal to 5, 25 into 10 raised to 3, 25 kilohertz, and 150 microhenry. Therefore, that is equal to the equation 0.889 amperes is the ripple current in the inductor ripple current. Therefore, delta IL. And similarly, the ripple voltage, that is the ripple voltage of the capacitor, or delta Vc is given by d I0 divided by Fs into C. The load current is given as 5 amperes. Therefore, D is 0.667 into 5 divided by Fs equal to 25 into 10 raised to 3 into the capacitor is equal to 220 microfarad, 220 into 10 raised to minus 6, or that will be getting, it is equal to 0.606 volt. Therefore, this is the delta Vc, and this is the delta IL, and this is the duty ratio of the boost converter circuit. Now let us see the closed loop control of boost converter. The circuit simulating model of that closed loop control of boost converter is shown here, and of course here the voltage, output voltage is sensed, and that is compared with the reference voltage, and that is given to a PI controller, and the PI controller output is compared with a sawtooth waveform, and that output is used to the trigger the MOSFET or the switch. Therefore, this is the basic simulating model of the closed loop control of boost converter. And here you will be getting it is set to 12 volts. Therefore, output voltage will be getting 12 volt independent of the input voltage variation or the load variation. For we'll be seeing in the next slide what is the output voltage when a voltage perturbation is given at the input side. Now continuing the closed loop control of boost converter, input voltage perturbation is done. For the reference voltage is set as 30 volts and the input voltage is changing from 20 volts to 25 volts. Here you can see that input voltage up to this one 20 volts, that is changing to 25 volts. But output voltage, reference voltage is kept as 30 volts. Therefore here as at this moment there is a small spikes is coming. After that it's again coming back to the 30, that is a reference voltage 30 volts. Therefore this is the output voltage when the input voltage is given as a perturbation from 20 volts to 25 volts. So that is a closed loop control of a boost converter output waveform when the input voltage is perturbed or that is changed. Now let us see an application of the boost converter. One application I am going to explain is the for maximum power point tracking control of a PV cell or photovoltaic system as such. Therefore, this is the photovoltaic array and this is the boost converter that already we have seen, inductor at the input side, switch is the diode is the capacitor is, and this is the load. Therefore, this is a boost converter and this is the PV array. And here if you plot the current voltage or IV characteristics of the PV array, this is the current voltage characteristics and this is called the of course the short circuit current and this is the open circuit voltage. And if you draw the corresponding PV curve will be getting, it is the product of current and voltage. If you take, then you will be getting power. So if you plot the PV curve, this is the PV curve of the PV array as such. Therefore this is the maximum power, this is the corresponding to maximum power. And if you plot here, this is the voltage corresponding to the maximum power is called the Vmax, and the corresponding current as such we can say that one here the corresponding current is given by Imax. Therefore the product of or VMP, actually it's max not max as such, VMP maximum here it is equal to VMPP as well as this is equal to IMPP, and the product of VMPP and IMPP is equal to the PMPP. Therefore this is the maximum power and this is the voltage corresponding to the maximum power VMPP, and this is the current corresponding to the maximum power. So this is the IV curve and this is the PV curve of the solar panel. And there is a one term to be explained, that is what we call it as, this is the maximum power, and corresponding to the maximum power, what is the resistance? In order to find out then to this point a line is drawn and the slope of that one represents the RMPP. RMPP means the resistance corresponding to maximum power point. Therefore RMPP is nothing but VMPP divided by IMPP. Therefore RMPP is the resistance corresponding to the maximum power point, which is equal to VMPP divided by IMPP. Therefore this is the RMPP and that is the resistance that is of the PV system or array corresponding to the maximum power. Now as in the maximum power transfer theorem we know that maximum power transfer occurs or the maximum power can be transferred from the source to the load once the resistance of this one from the source is same as resistance of the load. Therefore if you make the resistance at this point same as this RMPP, the maximum power can be transferred from the PV system or from the source into the load. Therefore in order to do this one, in order to make this equal value of the resistance, here the boost converter is being used here. Now coming to this again diagram, the resistance at the R out is represented as the resistance at the load side, that is the R out, and the resistance reflected at the input side of the converter, the resistance reflected at this input side because of an R out, how much is resistance is reflected at this point. We'll be deriving the equation in the next slide, which is equal to R in, that's called the R in, equal to R out, this resistance into 1 minus D whole square. Therefore by controlling the duty ratio, we can make the input resistance or resistance looking from this one same as the resistance of the PV array or same as RMPP. Once this resistance or the resistance looking at this point is made equal to this RMPP, the maximum power can be transferred from the solar panel into the resistance. Therefore, that is the basic concept of maximum power point transfer. Well, let us see the derivation of this one. Rin equal to the resistance at the input of the boost converter is equal to same as whatever this resistance R out into 1 minus duty cycle D whole square. Now continuing the MPPT controller using boost converter, as I already explained, the boost for the resistance at this point, looking from this side, that resistance is represented as, it is equal to here Rin. Now we are going to derive the equation for this Rin in terms of R out. For boost converter, we know that basic relation was already we derived. V0 by Vd equal to 1 by 1 minus D, and I0 by Id equal to 1 minus D. Already we derived that one. Therefore, V0 equal to Vd by 1 minus D, and similarly I0 equal to 1 minus D into D, or V0 by Vd, that is output this voltage divided by the input voltage. V0 by Vd is given V0 by Vd, or here V0 equal to Vd by 1 minus D and I0 equal to Id into 1 minus D, or V0 by I0, that is the resistance R out. V0 by I0 equal to R out, which is equal to, if you take Vd into Id into 1 minus D whole square, or Vd by Id is equal to the resistance at the input side Rin, or Rin into 1 minus D whole square, or R out equal to Rin divided by 1 minus D whole square, or Rin equal to 1 minus D whole square into R out. Rin equal to 1 minus D whole square into R out. Meaning that the resistance looking from this point, that is equal to whatever the output resistance R out into 1 minus duty ratio whole square, 1 minus D whole square. Therefore, we can adjust the duty ratio D so that this resistance Rin can be made equivalent to this RMPP, that is resistance corresponding to the maximum power point. RMPP equal to VMPP divided by IMPP. We are adjusting the duty ratio in such a way that this Rin is same as RMPP, then maximum power will be transferring from the solar system into the load. Therefore, that is the way in which the boost converter duty ratio is being adjusted. Now continuing the MPPT control using the boost converter, as I already explained, this is the circuit diagram of the boost converter. This is the PV array and this is the load, and this resistance reflected that is called Rin is the, and Rin equal to R out into 1 minus D whole square. Therefore, we are adjusting the duty ratio of the boost converter so that this Rin is made equivalent to this Rin is made equivalent to RMPP. Therefore, RMPP, that is the resistance corresponding to the maximum power, which is equal to RMPP is nothing but VMPP divided by IMPP. Therefore, adjusting the duty ratio of the converter in such a way that Rin equal to the resistance looking from this point is equal to R, which is equal to R out into 1 minus D square, 1 minus D whole square, R out into 1 minus D whole square, that is equal to the resistance corresponding to the maximum power, RMPP. Therefore, RMPP is the resistance corresponding to the maximum power point. We are adjusting this duty ratio such that this Rin is the same as the RMPP. Therefore, for example, it is shown here. Example, R out equal to 20 ohm. That is, here this resistance equal to 20 ohm. That is, this is the corresponding resistance. R out equal to 20 ohm. And RMPP equal to 13 ohms. That is the resistance corresponding to the maximum power point. That is equal to 13 ohms. Now what we have to do is, we have to adjust the duty ratio such that this one, that is Rin equal to R out divided by R out into 1 minus D whole square, that is made same as the RMPP, which is equal to RMPP. RMPP is equal to 13 ohm. Therefore, Rin equal to R out into 1 minus D whole square, which is equal to 13 ohm. And we know that R out is already, it is taken as this is equal to 20 ohms. Therefore, this is equal to here 13 ohms equal to 20 ohms into 1 minus D whole square, and the corresponding duty cycle D equal to 0.193. Therefore, if you are working this one with a duty cycle of 0.193, then this resistance at this point at the input side will be same as 13 ohm, which is same as the RMPP. Then maximum power will be transferring from the PV system into the load. Therefore, we are adjusting the duty cycle of this switch or boost converter switch in such a way that the resistance reflected at this input side is same as the resistance corresponding to the maximum power point RMPP. Then maximum power will be transferring from the solar panel into the load. That is the basic concept of maximum power point transfer or maximum point transferring of the maximum power using the boost converter.